What's up, guys? We're going to look at ionization in this video, and in particular, we're going to look at first ionization energy. So let's start off with our definition of this. Here, we're talking about the energy to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions. So a few things to really pay attention to there. It's this 1 mole of gaseous atoms. That's really important. So we're only ever talking about 1 mole of these to form 1 mole of gaseous ions. The gaseous is super important. So if we're going to draw an equation for this, it's going to look something like this. We've got Li, gaseous, reacts to make Li plus, gaseous, plus E minus. That's all we're going to have to do for any first ionization energy question. We're going to have to draw this equation. But it gives us a few clues as to what we spoke about last video in terms of electrons, subshells, shells, all of that stuff. And we can sort of look at this as we go through in this graph. So here, as we go through, I'm just going to draw the structure of atoms as we go, bearing in mind we've always got this positive nucleus on the inside. So we start off with hydrogen. There we've got a relatively low ionization energy, and we climb up to helium. We'll explain why, as we go across a period, why we do get this general increase, but it's basically because we've got a more positive nucleus there. We've got an extra proton. Now, to remove the next electron requires much less energy. And that's because now this is further away from the nucleus. We've got an increased atomic radius because it's in a further shell. We've got some electron shielding here. We've got very little change in the relative change in the strength of the nucleus there. So this is providing us evidence that we have these shells because we get this sudden drop here. As we go along, we've got beryllium and then to boron. Boron, again, requires less energy. And if we draw the electron structure here of boron, we've got helium, and then we've got a 2s2, and then we're down to 2p1. So what boron here is showing us that when we go to 2p1, this is slightly further away from this positive nucleus, and so there is a slight change here. So we can label this across here 2p1, so further away. And here, new shell. Now as we carry on, we go to carbon. Again, what we expect. We go to nitrogen. And now we have another dip with oxygen. And here, it's best for us to draw these electrons in boxes. So if we look at our 2p orbital here, we have this going on. With oxygen, we have 2p4. So what happens here is there is an electron pair, and so this repulsion is what causes this drop. So it's 2p4 electron repulsion is what leads to this change in pattern. And then as we move on, fluorine, as is expected, neon, as expected. I didn't draw oxygen on. So these are our 8s, and then we have a big drop down again to sodium. And that again, we've got a new shell. This is evidence for what we spoke about there. Let's move this to explain that. Perfect. Now, we've got general patterns across the periodic table as well. Here, we've got decreasing ionization energy. Actually, let's just change the arrow. And there, very simply, as we move down the group, we're starting off with small atoms and they're getting bigger and bigger and bigger. And so at that point, as we move further down, the electron being removed is so far away from that positive nucleus that very little energy is required to remove that. So increasing energy here as we go down, because as we go down the group, atomic radius increases, therefore less energy needed. Now, as we move across here, as we move across the periods, we've got increasing ionization energy there. And that's because as we move across, we're getting more and more positive protons inside here. And very little is happening to what we call electron shielding. And we'll talk about this sort of stuff later on. So say if we've got our group 2, or period 2, sorry. We've got our positive nucleus in the middle, our electrons there. So let's start off with lithium. So here, there are only these 2 electrons that are in the way of this positive nucleus. This electron shielding is always going to stay the same, but as we move across, we're adding electrons, but we're also adding protons to the middle. And what this does, the positive pull of the nucleus decreases the atomic radius. So there, we've got increasing ionization energy because more protons or higher nuclear charge which leads to lower atomic radius, therefore higher ionization energy. Perfect. So, only thing I want you to do here is this. First ionization energy of magnesium, circle which one of these you think has the highest ionization energy and explain why. Beware of the sets of exceptions. You need to think, are we talking about these sorts of patterns, or are we talking about the exceptions which I've spoken about here? Let's look back at the previous video. Here, fluorine. Fluorine, remember, 9, 1s2, 2s2, 2p1, 2, 3, 4, 5. So we can do He, 2s2, 2p5. F minus, so 1 electron gains, 2s2, 2p6. Copper, remember, one of our exceptions. So start off with Ar, 4s2, it would be normally anyway. D1, 2, 3, 4, 5, 6, 7, 8, 9. But this is one of our exceptions where this is filled first. So we've got 4s1, Ar, 4s1, 3d10. Next, remember S fills first, not in the case of copper, but it also empties first. That is the case in copper. So we get to Ar, 4s0, though you don't need to write that, 3d10. Aluminium, is here. So we can start off with neon, 3s2, 3p1. And Al3 plus, we can just do any. Thanks guys, happy revising.